Okay, so let's go over how to solve a 2D truss system using finite element methods. This is kind of a continuation of what we did last time in the one-dimensional FEM. The problem that we have right now is this one. So we have 3 nodes and 3 elements. Node 0 is fixed, so it cannot move this way, it cannot move in the x or y direction. Node 1 is fixed, is on a roller, so it can translate this way, but it cannot move in the y direction. And node 2 is free to move in either directions. If you look at the loads, there are unknown reaction forces here. So there is reaction force at node 0. There is reaction force at node 0 that we do not know. There is a reaction force in node 1 that we do not know. And yeah, that's pretty much it. So how about the other parts? The other parts, we know the force applied here is 0. There's no force applied here in the x-axis. There is a force applied here in the x-axis for node 2, but in the y direction there is no force applied. Okay, so that's pretty much it. This kind of defines the problem. The end goal is to find the unknown reaction forces. The unknown reaction forces, these 3, and the unknown positions. Okay, so which is this one, and this one. So 3 reaction forces and 3 unknown displacements. Okay. So the first step is to tabulate the information that is shown in this figure. Okay. So we need to make 2 pandas table. One contains the nodes information and the other one contains information about the elements. Now within the nodes table, you will have to define where the node's x coordinate and the y coordinates are. What is the node's displacement if it has a displacement? If it doesn't have a displacement, you have to set it to np.nan, okay, as a placeholder. And the same thing for the load. If it has an applied load, or if it doesn't have any applied loads, it's a reaction load, then you have to set it as np.nan. Okay, so let's do that first. So we have, now let's look at node 0. So node 0 is going to be the first row. So the coordinate, if you take this as your origin, you take this as your 0, 0 point. So that's your origin. Then the first node's coordinate will be 0, 0. Displacement is, we know that it's not going anywhere in the x direction, so it's 0. It's not going anywhere in the y direction, that's also 0. And we do not know the forces in the x or y direction, so np.nan. Okay. And we'll call this our nodes table. So make sure your libraries are defined first. Run this. That's your nodes table. How about your elements table now? Let me just copy this. Element 1 or element 0 starts at 0, ends at 1. So 0, 1. And the area is 2, material is 10. So 2 times, so let's put everything in SI units. So this is millimeter squared. So times 10 to the power minus 3 times 2 minus 6. And I think you can just say E minus 6. And material is 10 gigapascal. So 10 E9. 10 E9. And that's our elements table. Okay, so it seems to be correct. Next up, we need to find the length, stiffness, and also this matrix, the rotation matrix, okay, for that particular element. And this will change depending on the angle of the element. So we'll have to find the cosine and sine as well. So let's look at how to do this. Now, in order to find the rotation matrix, you need to calculate the cosine and sine, and you don't have to solve for the angle. You can find cosine and sine directly from delta x and L. Delta x is the difference between the x position of the start and end node, and the same thing for delta y, and L is the length of the element. Okay? So you can use all this information to come up with the R matrix. The length for the element is given by this formula, and you also have the formula for the stiffness. Okay, so in in Python, the last time we used the apply function, we found length and stiffness separately. In this case, you could just use one function to provide everything, because we have values that you kind of reuse so for example, you'll find length over here, but then you use length and delta x here to find R. So we can do all of this inside one function. Okay, in that case, instead of so you would return, for example, the length, the stiffness, and the R matrix. Okay, so in your elements table, for example. Okay, the only thing that you have to keep in mind is when you do this with the apply function, the keyword argument result type should be set to expand, otherwise it doesn't work. Okay, so if you set it to expand, it will take all these three outputs and then split it into the three columns that you want. Okay, so now let's compute the length, stiffness, and R. So length L is np dot square root of delta x squared plus delta y squared. Delta x squared plus delta y squared. So we'll go in reverse. Okay, so this is my length. So what is delta x? So delta x, delta x is the difference between the end node and the start node. Okay, so delta x is going to be, okay, so now we need to define what x coordinate and x coordinate start, all these things mean. Okay, so x coordinate of the end node is, you can find it from the nodes table. So you can go to the nodes table and give it the end coordinate, and what you want to get is the coordinate x from that table. If you remember, this is what the nodes table looks like. So within the nodes table, you can give it the node index, and it will give you the coordinates and the coordinates that you need. So coordinate x and y. So we say nodes, this should be nodes dot location. You want to get the only for a particular node. Okay, this will give you the x coordinate. Okay, there are better ways, or there are simpler ways, and you can do this, but I'm trying to spell out everything so things are clear. Okay, so we have the coordinates. Now we just need to define what is our start and end node, and that's easy. We know start node is from the elements, or in this case, row is each element. I can call this element then. Okay, so remember that this is the elements. So all the elements, and when you do the apply function, you're computing it per element. So each element, you look at the start node and then calculate the length and so on. Okay, so this is from the element, you only want the start information, and from the element, you want the end information and coordinate. Okay, so that's how you can find the length. So everything is defined all the way up to the input. Okay, how about stiffness? Stiffness, we haven't put it inside the elements table, so just call it length. And then finally the R matrix. So for the R matrix, what do we need? We need to do this cosine sines. Okay, I'll just call it C and S so that our life is easier. So np dot array. Okay, so I wrote down the matrix. Now we have to define what is cosine and sine, and we know cosine is delta x divided by L. So delta x divided by length. Okay, so this is why we wrote everything inside the same function, so that we have access to these variables. Otherwise, you would have to recalculate everything and then find cosine and sine. And that's pretty much it. So if I run this and check the elements table, df. So this is not df. We need to have it apply to the elements table. There you have it. So we have found the length, the stiffness, and the R matrix. Okay, now we have all the information we need. We need to put it together and assemble the global stiffness matrix. So this is how the local equation looks like. You have the stiffness multiplied by the R matrix, and that they form the coefficients for your displacements, and this will equal to your loads. Okay. This, for each element, this is the position it holds, and you have to then plug this into the right place in your global stiffness matrix. So how do we do this? So just to make sure that you understand the mechanism behind this, let's just look at one element. So let's say this is U1, V1, U3, V3. Okay, so let's say you're assembling the global matrix. In the global matrix, you will have to consider U1, V1, U2, V2, U3, V3, and however many nodes there are, you'll have that many displacements. Okay. So now, where do we put this? So the first value is going to be Ke times Cs squared. This number, so just always remember that the Ke is multiplied here. This number has to go to the position 0, 0. Okay, because it has to do with U1. So it's gonna go here, Ke C squared. Okay, the next number is going to be the one after it, so Ke Cs. Okay, the next number minus C squared Ke will come at position wherever you multiply with U3. So not here, you skip this one, you skip this one, because these are for U2 and V2, and then you go to the next position, so it's going to be Ke, so minus C squared, and the last one would be negative Ke Cs. Is it clear? So you can kind of imagine the position. So it's going to be 0. Okay, so the position here is 0, 1, 0, 0, 1. Then you skip 2, 3, and then 0, 4, 0, 5. Okay. It's a bit complex. If you want to do this manually, you will have to write a code to place all 16 values here. Okay, so this is going to be time consuming. So instead of that, you could make use of NumPy's the index function, or ix underscore function, to do this for you. But you have to be clever about this. Okay, so let's look at how you would do this. Okay, first thing you need to note is that when you make the global matrix, you have to make sure you have a system that you follow. So in this particular case, I could have come up with any system. I could have done U1, U2, U3, and then V1, V2, V3. So depending on that, your global stiffness matrix will change. So always have some convention you're following. So we'll stick to this convention here, U1, V1, U2, V2, U3, V3. Okay. Okay. So in this case, what's going to happen is the first node, the first node is this one, the next node is this one, the next node is this one, and so on. Okay, so I'm going to follow this convention. So so in order to get this done successfully, you have to have a way of saying, for example, if I'm dealing with node 2, I have to get the indices, so the 0, 1, 2, 3, 4, 5. So if I say I want to know the positions for node 2, I have to get the information 2, 3. Okay, this will tell me exactly which rows I need to deal with. Okay, or if I say I want to know the location of node 3, okay, it has to give me 4, 5. So how can you do this? What you could do is you could create this vector first. Okay, and then you can reshape it into 0, 1, 2, 3, 4, 5. And then if I say I want this node, I can get that information from that matrix. Okay, that's what we're going to do here. So I briefly mention it here again. So So how large is our global stiffness going to be? It goes back to the number of nodes that you have. Okay, so we have 1, 2, 3 nodes, and each node will have the x and y displacements, and so you will have in total 6 displacements. Okay, so that's 3 times 2. So in the code we can say find the length of the nodes and multiply that by 2. Okay, that's the total number of total size of the matrix that we're going to see. Okay, so in our particular case we would have 3 nodes, so 0, 1, 2, and in the table it will be u1 or u0. Okay, so first we make array 0 to 5. Okay, and then you can say dot reshape. Okay, so you can reshape it such that it has 2 columns, so you'll get this information here. Okay. Next, we need to create the global stiffness matrix K. So K equal to. Okay, so it's going to be a 6 by 6 matrix. Now we need to place in the index the right information. Okay, so let's see if we are getting the right information or not. So for the first element, so we need to use the np.ix function, but we need to provide it with the rows and columns. Okay, so that it can go and fetch the right places in the matrix. In a 2-dimensional case, it's not going to be just 2 numbers, you will have 4 numbers like we discussed. Okay, so you're going to change 1, 2, 3, 4 positions. Okay, and that has to do with the start node, which has 2 positions, and the end node, which has 2 positions. Okay, so what you could do is you can get the positions for the start node. So let's assume it's 0, 1 in our case. And you could get the position for the end node, so 4, 5. Okay, then you can combine this using the h horizontal stack function in NumPy, so it will become 0, 1, 4, 5. Once you have that, you can just provide this to your np.ix function, and it will do the indexing stuff for you. Okay, so here we take the element. We want to know where does it start. Now, after reshaping, make sure you put it back in indices so that we can use it. So if I say indices start, I'll get 0, 1, and if I say indices end, I will get 2, 3. The displacements are located in position 2 and 3 for the end node. That's what it says. Okay, now we need to combine this start and end together. So I'll have indices equal to h np.h stack. Look at what the indices look like. So there you go. So it combined it properly. Now you can use the np.ix function, indices rows and indices columns as well. Okay, so this will generate the right coordinates in the matrix for you, or indices in the matrix for you, so that you can manipulate the global matrix. Okay, so just to see how this works, we're going to index K at this position. We'll set everything to 100 so you can see which positions we were able to change. There you go. So it's the right position. Okay, you will again check another element. For example, element 1, you can see it's in this corner, and element 2, the last element, will be in these corners here. Okay, so everything seems to be working fine. All we have to now do is combine this and make a function out of this. So do this again. So we're not pushing in 100, we are pushing in the value, which is going to be element stiffness multiplied by element the R matrix. Okay, and then return K. Okay, now the global K. Okay, local variable indices reference before assignment. Oh, okay, so yeah, we'll just put this inside the code just to avoid this error. There you go. Okay, so yeah, so we forgot to remove this line over here. So it's resetting it and just putting it only for the last element. Okay, so don't forget to remove this line so that it refers to the new incoming element every time. And yeah, so you have yeah. Now that we have the K matrix, you can now solve the rest of the problem just like we did last time. We have to first partition it into the 4 parts depending on where the unknowns and knowns are located. So we did that here last time. The only difference is instead of having one unknown displacement, you'll have to figure out where the unknown displacements are in both the x and the y direction. What does this mean? So let's look at the nodes table again. We need to figure out where the unknown information is. So unknown displacements, for example. But for that, we need to have this in the same format that we agreed upon in the beginning, okay? Which is, it's going to be U1. So what we can do is we can take out the 2 columns that talk about the displacement. So that's x and y. We'll convert it to a numpy array. Okay, so this means you will get an array that looks like this. Okay, but then we want to put it in exactly this form. So if you put it in this form, it's going to be 0, 0, 0, 0, then unknown. Ravel basically converts it into like a one-dimensional array from a two-dimensional array. Okay, so let's look at it. So that's what it does. It takes both the columns x and y and then makes it into a one-dimensional array. Now it's easy to find the index for where the unknowns are. So you can say is nan. You can just say np.isnan and you can give it the matrix and it'll tell you where the unknowns are. Okay, so it's unknown here, unknown here, unknown here. Okay, that gives you the index of where things are unknown. And you could then also do the same thing for the load. Okay, P will just be the opposite of this, so it's going to be true, true, false, true. Okay, so true, true, false, true. Yeah. So it seems to be working fine. So we have the A and B matrices. You can now do the partitioning just like we did last time. So I'll just get the code from last time and just place it here. Okay, so this is the code, and we can then see that we have extracted a 3x3 matrix for KAA, which makes sense. And it seems to be working fine, so let's move on. To solve it, again, we just follow the same equation that we had last time. Okay, so we have solved effectively the problem. So we have the entire U vector defined. So we got all the displacement, and you also have the entire P vector. So we solve for all the forces as well. Now we need to know how to put this back into the table. Okay, because now this is a one-dimensional array. To put it back into the table, we are looking at the X and Y columns. You could again do this manually or in different ways. But one way I'm going to do it is I'm going to convert this back. I'm going to reshape it back into a 2D array and then put it into the table. So to reshape it, you can just use the reshape function, and you can say -1, 2. -1 means you don't really care about the number of rows, but you care about the number of columns being 2. Okay, so that's reshapes it this way, and then you can put it back into the nodes table. So again, you don't want to affect your nodes table because if you want to repeat this code, then things will get messed up if you redefine your nodes. So instead of that, we will create a results data frame which is equal to nodes. Now in Python, you shouldn't do this because Python does not create a copy of nodes. It just refers to nodes using a new address result. Okay. So if you really wanted a copy, you should say copy. Otherwise, whatever changes you make to results will also change in nodes. Okay. And then you can say result equal to, it's not P, it's U is the displacement, dot reshape. Okay. So there you have it. So it plugged in the numbers here for you. You can do the same thing for the load. So copy this. Instead of U, we'll say P and load. Okay, so I plugged in the loads and the displacement. So basically, this is the solution to the problem. Okay, all your unknowns are now known, so that's the end of the problem. Now, sometimes you want to plot it so that you can visualize this result rather than just seeing it in a table. So let's look at how you can plot this. So first you need to, we only have the displacements that we solve for. We need to find the deformed shape. Now, what is a deformed shape? Deformed shape is the original coordinate plus the displacement. Okay, so that's a deformed shape. Now, we will add a factor here because sometimes these displacements are small and it's not easy to visualize them. So we'll add like a scaling factor. Okay, you can play with this to make the graphs a bit more clear. Okay, so yeah. So instead of data frame, okay, I'm going to replace data frame with our results table. So result, call the result, right? Yeah. Okay, so this seems to be working okay. So this is node 0, node 1, and node 2. Okay, maybe the factor is a bit too much. Let's check the original one first. Yeah, yeah. Okay, so now we want to. Okay, so this is not the original. The original would be the coordinate itself. So coordinate x and coordinate y. That's the original position. And we'll then make a copy of this to plot the other one. And deformed x and deformed y. Okay, and we'll change the color from red to blue. And this is deformed. Okay, so now you can see the deformed shape. Okay. Again, if it's not clear, you can increase the factor a bit so that you exaggerate the displacements. And this is the shape. So you can see node 1 is not going anywhere. Node 2 is, or node 0 is not going anywhere. Node 1 is slipping in the x-axis, and node 3 has been displaced in both the x and y axis. Okay. And that is. Now, if you want to make a connection between the last point and the first point, what you could do is you could re-add the first point to the end of the pandas table. Okay, so let's say result, I'll add this as result dot location, so 0, 1, 2, 3 equal to result dot location 0. Okay, so it just repeats the first node as the last node. Okay, and you can add a legend as well, plt dot legend. Okay, so there you have your final solution. Okay, I hope it's clear. Thank you.